Okay, I see that's not the one. This is the one. Yes, yes. And, I see. Oh, wait a second.
The big one advances forward. The
Okay.
smaller one backward, and the top is this big thing.
Oh,
that
let's
moves.
see. Oh, yes, I see. Okay. Well, we'll see if I can remember that. So it's a pleasure to see you all this morning. Thanks for coming. Please interrupt me, ask questions, make objections. The best questions are something often, what does this have to do with, or things like that. Because if you don't understand it, chances are one of your colleagues here also doesn't understand it. And in fact, you may discover that I don't understand it, so which is itself a good lesson to get. These lectures I have, I'll be giving one in each of the first 3 mornings, will overlap with other presentations at the school. It's a mixture of very elementary quotes, intuitive, or at least my intuition anyway, approaches to things which hopefully will complement the more in-depth presentations about the structure of the proton, about lattice approaches to quantum field theory that you'll get from other lectures. But again, as the next couple of days goes on, if you hear something in another lecture and want to relate it to something that I've said, just at any time, and let me know. So these lectures are called Introduction, QCD, and Electrons. I mean, electrons being the E and the EIC. And so it's natural to put these together. So what the outline of this little thing, let's see if I can get this blob to work. Oh yeah, down here. There are 6 topics, and in some sense, it'd be nice, I'll aim at covering 2 of them in each of the lectures. So the first 2 today are very introductory: review, light and photons, the hidden universe. And what I call here the game and stories of quantum fields, because this is the tool. Quantum field theory is the tool, for better or for worse, it's our best understanding of the universe as it lives today. I mean, string theory is there to provide us with quantum field theories with which we can confront nature. Or any other quantum gravity description. The success of any such big description so far is in terms of providing the quantum field theories that describe the nuclei, that describe the motion of electrons, and also the weak interactions, because the standard model. Of course, this is all the visible universe. There's an invisible dark matter, dark energy that, well, we won't primarily be talking about that in this set of lectures in this school. But of course, it's there, and I'll touch on it briefly. Any questions before we get started? Okay, I've got a question. How many of you would describe yourselves as experimentalists? You're a brave bunch. Okay, so I suppose everybody else is theorists. Would somebody else like to say they're neither of those two? So I can. Okay, good. So please ask experimentalist questions. That's the thing. They're very often the best. All right, now, first advance of slides. So I think we have about 20 slides today. So you can see the numbers at the bottom. I haven't figured out yet how to have, what I really like, I think I saw it in a talk by Martha Constantiu, that she had her page number and then the total number of pages. This I'd love to learn how to do that. I don't know. So if somebody knows, don't tell me now, but you know. Okay, so light and photons. So really, if we think about this in the big picture, it's not, it's old and it's not that old, depending on how you look at it. The wave theory of light, said Einstein in 1905, 120 years ago. And I can tell you, young people, that's not that long. You'll see. Which operates with continuous functions, the E field, the B field, Einstein had in mind, has proved itself splendidly. And this little picture here is supposed to remind us of that by showing a diffraction pattern. But then Einstein went on, and I went on a little bit. Oh, God. Yeah, here we go. Okay. So Einstein went on to say, and this is really building on the insight of Planck for black body radiation, should keep in mind, however, that optical observations apply to time averages only. The energy of light, he claims, is localized at points in space and can be absorbed or generated only as a whole. And those things that are absorbed or generated only as a whole are, and you know the name.
Photons.
Photons, right? Okay, it's great to hear your voices. I just want to tell you, you know, that otherwise I may fall asleep. Of course, you're entitled to fall asleep, but I'm not. Alrighty, so, and why was that? And he came to that conclusion, which was absolutely revolutionary conclusion. If you think about it, everything else that we do, and we build these giant machines like the EIC, is built upon that observation. He was building, in turn, looking back on the photoelectric effect. Now, it's very interesting. We normally think of Hertz as being the great demonstrator of Maxwell theory, showing that there were waves associated with were generated by electric currents, that those waves traveled at the speed of light and followed Maxwell's equations, and therefore electromagnetic waves must be light, in addition to other radiations on the spectrum. So this was in a paper, and actually Hertz he didn't really live long enough to do much with it, but the photoelectric effect, if you think about it, it's not really that long. It's 1887 to 1905. So it took less than 20 years for this tremendous, and what he says is, I mean, you can see the words here, it's a little bit dark. 2 electric sparks were produced by the same discharge in an induction coil. Sparks were produced at the receiving end when there was a big spark that generated the electromagnetic wave, and then at the other end, there were sparks of the receiver. That's not what he was after. He was just wanted to see some currents flowing. But actually, electrons were ejected from the material. And so that was something that underwent various studies, and enough so that Einstein could make the famous photoelectric effect observation. And so the idea is the density of photons is proportional to the square of the wave amplitudes, but they remain indivisible photons whose energy is characterized by their frequency. So E equals what letter? H. And now going to another alphabet, nu. Okay, so that's page 2. We're 1/60th of the way through. I go this one. Page 3. So again, with these very general observations, this invention of the concept is realization that fields manifest themselves as quanta is set the stage for many great discoveries in the 20th century. All matter, including photons, is described in terms of particles that are created or absorbed at infinitesimal points. And infinitesimal points is a concept on which the whole reason for building the EIC rests. It's the interaction of the electromagnetic field with hadronic matter should happen at a point described by an electric current. And everything in DIS is current correlations, current amplitudes generated by currents. We'll see those as we go along. Okay, it's this idea of infinitesimal points that's characteristic of local quantum field theory. And locality, the concept of locality is really this concept that things happen at points. It's a crazy idea. You think, well, a bunch of points have to sort of agree together, to do it. But we take it to the, as it were, to limiting case. At longer scales, these particles can combine into what we call emergent systems like light waves. So it gives quantum field theory stories, and that's a term I like, and we'll come back to it again. And here's a story, which is a famous one from now over a decade ago. The story which involves QCD, the energy supplied by two colliding protons, manifesting itself in terms of locally, in terms of two gluons, which merge by creating a top loop, which then couples and produces a Higgs particle. That's the H here. And then the Higgs particle decaying into one pair, and then one of them is a virtual Higgs particle, Z. The Higgs decays to two Z's. One of the Z, both Z's go to E plus, E minus, E plus, E minus. And that's what this thing looks like. Okay, this is what the detector saw at CERN as one of the events, which put together showed the existence of the Higgs boson. But there's this direct, as it were, representation of this final state in terms of this story. And notice, by the way, it's this story, but up here there's a 2, right? And then there are these vertical lines. And that tells us that all of these stories are stories for an amplitude, but the amplitude we can't get at directly. It's the square of the amplitude that we work with. And by putting together different kinds of final states, which have different squares, we can sometimes work back to the amplitude itself. And that's something which is done in cases like off-forward. You'll hear the terms off-forward distribution, or rather amplitudes, so forth. Okay, so these are, in some sense, the triumph of this concept of quanta describing fields. One triumph, but it was a big one. So emergent degrees of freedom, when you put the quanta together, they're a universal feature of both classical and quantum laws of nature. At the scales we can see, from hydrogen gas to galaxies and stars, so these are giant things, from atomic magnetic moments to antiferromagnetism, so other magnetic properties, from molecules to phases of matter, from electrons and metals to superconductors, and in fact, from chemistry to life itself. And this is a Rousseau painting here, but well, very well. And at the micro scales, and this is where we begin to approach the subject of all this, which is the electron-ion collider, from protons and neutrons to nuclei. And of course, we know, coming to this school, that the protons and neutrons themselves are emergent collections of quarks and gluons, and then also virtual quark pairs. So here, this is just a representation of the decouplet of baryons made out of protons and rather quarks. At each step, the compound system has features which are qualitatively different than those of the constituents, and yet those features follow from the properties of the constituents, from these point-like properties in terms of currents, in terms of fields, to these collective objects already at the level of the proton, which, we're in the process of studying. All right. So currently, everything we can see and in quotes, but in some sense, C meaning all the stuff that's not dark matter, or never mind dark energy. Actually, it isn't really clear, at least to non-cosmologists like me, that dark energy is a thing. Dark energy is a description of what seems to happen in the universe as it evolves since the Big Bang. So far, it's not dark matter, as fuzzy as the concept is, it's kind of a thing because you can see it's different here than it is there. It's near in the halos around galaxies, collections of galaxies. You can see there's more of it. It affects the way light passes through there. So you can say, okay, it's there. I know it's there. Not so much over here. But dark energy, it's like, it's what's happening everywhere. So anyway, that's kind of an aside. So it's not so obvious that there's a point-like description of dark energy. And it's not so darn obvious there's a point-like description of dark matter either. But most likely there is, or at least many of my colleagues spend a lot of time trying to find those point-like interactions. So, but going back to the things we can see in terms of, it isn't much by the energy budget of the universe, people say, but it's like real important to us. So let's be selfish about this. All these things are made up of the matter and force particles that are playing in the game of the standard model. And I'll say again what we mean by game. In some sense, that's what I'm trying to cover in this lecture today. So here they are. The baryons are made of 3 quarks, up, down, and up and down. Basically, out of 2 of the kinds of quarks, the mesons, the quarks, and the antiquarks. We have in our everyday life, you might say, these are the force particles, the gluon and the photon, combined, of course, with the Higgs boson, living in splendid isolation as the only particle without spin. Scalar particle, that is. So that's kind of interesting. Well, anyway, what's that there for? Well, it's there to kind of give mass, some of the mass, kind of starting down payment on mass, but the rest of the mass is coming generated by QCD itself. That's to some extent what we're talking about in the school and in the whole project of the Electron-Ion Collider. And of course, before it, Brook, which is running down after 25 splendid years. And of course, the electron and its the electron neutrino, the neutrinos, electron and muon, we don't see them, but they're all over the place. And in fact, is there a signal of the way that the sun generates the energy by which we get all the photons we need, at least 12 hours out of the day on average. So the fermions carry this. Let me see, I'm still trying to get used to this. Fermions carry spin 1/2, the basic quantum of angular momentum, and the force particles carry spin 1. Their spin directions can change, but they never, ever slow down. This is kind of amazing when you think about it. I mean, as the angular momentum, they just don't get tired. Well, yeah, okay. So mysteries of nature. All right. And so again, looking at the same chart here, up in the left-hand corner of that nice chart are the strongly interacting fermions and their gluon, QCD. Then we get when we go to electromagnetism, quantum electrodynamics, QED, we add the charged leptons, and of course the photon, and finally the weak interactions. We go all the way down to the neutrinos, and we add the Z boson, the W boson, and the Higgs. So the Higgs is only living with the fermion, the weak force. Okay, so the strong, the electromagnetic, and the weak being the basic forces of the standard model. And of course, all of these are discussed in are variations of non-abelian gauge theories, which were famously discovered at Brook on Long Island by C.N. Young and Robert Mills. Okay, so where this title here is Where Have They Been? The Three Unseen Realms. So this is like, we don't have much time, so let me just give the story of the universe. Right after the Big Bang, okay, before that, well, all right, there were other summer schools for that. All particles mixed freely at very high temperatures. Decays were balanced by production, but as the universe expanded and cooled, high energy collisions ceased because there were fewer particles were further apart, and they were kind of going down in temperature as a result. So heavy particles decayed and were not replaced, and are now found only in short-lived virtual states. What do we mean by heavy particles? In this case, the heavy quarks. We assume the Higgs did whatever it does to give masses to the quarks, at least the heavy ones. You know, how the light quarks get their masses, it's probably the Higgs mechanism, but we don't have the direct evidence that we would get, say, for the top quark, the bottom quark, and to some extent the charm quark and the tall limit. So the heavy particles, they're not here. And yet, being in quantum mechanics, the world is quantum mechanical, they are here. They're here all the time in virtual states, which live only short periods. It's like 1 over the energy that would require to create that state, but that you don't have. Like we don't have it here. But in here, top quarks, bottom quarks, charm quarks, all the time. But we don't get to see them. If we take this, somehow put it at the LHC, we bring them to life. This is kind of how it works. So that in words here, heavy particles decayed and and were not replaced and are now found only in short-lived virtual states from which they can only emerge with sufficient energy before decaying once again. So this is part of the standard model and presumably other components of quantum field theories that describe dark matter. This is how you make them. And that's what accelerators are for. Yet other components of the universe appear to be hidden from us by not sharing electricity and magnetism, QED or QCD. This is dark matter, but it's entirely possible that they have the weak interactions, and that's how you hear about weakly interacting massive particles, WIMPs, and things like that. Stable quarks and gluons retreated. So these are the quarks in the up and down quarks. They retreated to the tiny volumes of protons and neutrons, surrounded at great relative distances by electrons and photons, and then not to mention the cosmic differences between the high concentrations of matter that we encounter in the universe. Theorements and theorements and theorements and theorements and theorements and theorements in each of these realms. So we use the players of a certain game, which is the quarks, gluons, electrons, and photons. And quantum field theory provides the rule. So for Jefferson Lab, for example, electrons are accelerated around the loops, nucleons await them in the experimental holes. I don't know how the nucleons feel. They say, you know, 10 to the minus 8 seconds ago, there were a lot of electrons going very fast. Watch out. And see, that's the whole point about physics of this. They can't see them coming. When the electrons are coming in at high energies, even the 10 GeV that you can achieve at Jefferson Lab, they're really relativistic. So by the time a signal could come from them, they're right on top of it. And that insight is what leads to the analysis that we talk about for high energy collisions at EIC, at JLab, at RIC, at the LHC. Okay, it's that you can't see them coming because they're coming too fast, right? Okay, so the idea here is quantum field theory systematizes the kind of duality between fundamental and emergent, and we use each to explore the other. We use collisions of emergent objects like protons to discover the elementary fundamental degrees of freedom inside the protons. And someday, in fact, if we find out that, yeah, the electron is really also made up of what they used to call them preons, but it's kind of fallen out of favor. Well, at high enough energies, one might be able to see that. Okay. So higher energies will require colliding beams, and that's where the EIC comes in. So that was the first part. Very fuzzy, but I hope it was fun. So anything come to mind? Like, when is coffee? Anything else? All right. So what I'd like to do in the remainder of this first lecture is give this little outline of what I like to call the game of quantum fields. And the rules are equations that govern the visible universe. That's not bad. So, and here's the basic rule. And the basic rule goes by the name that I'm sure you've seen, the Schrodinger equation, okay? And it says, well, really, you start out with an amplitude. If you have a list of particles that describing your picture of the universe or some part of the universe at time, say capital T, and you'd like to know the amplitude for having a new list of particles at time T plus delta T, what you do is you take the original list and you multiply it, or you act on it with a rule for changing the list, and you multiply by delta T. So if you divide by delta T on both sides, you can turn this into a differential equation. So these rules here are the rules that act on any list of fermions and bosons. And we represent the list in terms of quark or lepton with an arrow telling you which way the fermion charge goes, an antiquark or antilepton with the arrow in the opposite direction, photon or weak boson is a wavy line, gluon is a coiled line. Needless to say, these pictures here are not exactly fundamental in their own right, but they're generally agreed upon kind of notation. So the list of particles is a possible configuration of the fields associated with these particles. So the fields tell you where these particles might be. A general macroscopic field is extremely complicated collection of these. Nevertheless, at each time, there are, as we say, a list of particles. That's the picture that we have in quantum field theory, or at least, as I would call it, perturbative quantum field theory. And we'll talk a tiny bit about this difference between perturbative and non-perturbative as we go along. Oops, okay. So these are the beautiful theories of the Standard Model, and they are just this series of how to change the list, or to say or put in technical language, the interaction Hamilton, or Lagrangian for the purposes here. We won't worry about those fine points. All right, so here are the rules for the electromagnetic strong and weak forces. They're each proportional to a charge. The electric is, of course, E, which is the positron charge. Somehow or other, I'm told that Benjamin Franklin shows the electron, what turned out to be the electron charge, to be negative, and we've been stuck with it ever since then. So E is the positron charge. The strong force with a charge G sub S and the weak G sub W. And the rules are rules either for 3 particles that involve 3 particles, or they're rules for 4 particles, all connected at a point. And here's this locality. These are the points that Einstein envisioned in its most elementary form, the points where we could produce a photon. And where does that happen? Well, in particular, it's right up here in the lower left. Here's an electric charge, say a quark or an electron, and a photon couples to it at a point. So these bring us back to the very first advances in concepts. Gluons come the same way from quarks and antiquarks. The gluons famously interact among themselves in SU3 in the standard model, and the non-abelian portion of the electroweak vector bosons also interact through the 3-point. And then we also have 4-point and these 3-point and the 4-point are characteristic of the Yang-Mills theories for the strong and weak interactions. Now, of course, Yang and Mills didn't have all of these. These came out of the experiments of the 1970s, the 1980s into the 1990s, which established the standard model on firm footing, which then allowed to build up to the production of the Higgs, which kind of completed all of the particles in the standard model. But again, should say not everything in the standard model is so well understood. In particular, the coupling of the Higgs to the lighter generations, the lighter, of course, the up and down to the up and down quarks and to the electrons and the muons. Still, to a large extent, to the most part, not known or not experimentally confirmed. We may know it or we may not, depending on if it's the standard model that was originally written down. So it's, of course, since it was realized in Dirac that if you wanted to have, by Dirac, way back in 1928, if you wanted relativistic invariance, these pictures here have to allow time to flow in any direction. And in particular, by looking at different time flows, you automatically include both particles and antiparticles. You take one arrow and you turn it in the opposite direction by rotating it. And sometimes you get an arrow going one way, an arrow going the other way. So if we have rules for 3 particles, they imply pair production and antiparticles, and also in the opposite direction, pair annihilation. And so again, if we have, say, the 4-particle interaction, the 4-gluon interaction, this is really 1 gluon going to 3 gluons, and even no gluons going to 4 gluons as in a virtual state because there's no energy, but you produce a particle with a list of 4 particles, which lives for a little while. And then if you're lucky or unlucky, you can bring that into the final state by giving it energy as we go along. We'll see that in a second. Okay. So these are, I hope, somewhat familiar. So yeah, here they are. All the different kinds of things you can have. So these rules are very, very flexible. There aren't many of them. They're all in this, let me see. Yeah, in these, I mean, they're 1, 2, 3, 4, 5, 6. But each of these has a number of different processes, depending upon which lines are in the initial and which in the final state. Now, again, I want to emphasize that by applying these rules, you go from one list of particles to another list. The simplest being you start out with an electron, and then you apply this upper left-hand corner in QED, and you end up with an electron plus a photon. Or alternately, turning it around, a photon might arrive at an anti-electron, positron, and then produce a state with a single positron, or the same with an electron, and so it goes until you're sick of it. Okay, moving right along. Here's how it works. So these are the stories I was talking about. There's a kind of restlessness in nature. I think it's good to think about it that way. And I was pleased that I saw there's actually a book by Max Born. It was kind of an introductory physics book written around in the 30s. And it was called The Restless Universe. I think it was just perfect description of what goes on in this picture of the time development of the universe according to perturbative quantum field theory. So here's the idea. Every single particle is constantly trying, I mean, to the extent that, I've been living with this stuff for so long that to me, Quarks are little people. You know? I mean, they each have their own personality, it changes. But anyway, every single particle in quantum field theory is constantly trying to unwind the whole world out of itself. And at the same time, to ravel it back up again, take everything it's given back. Always through the simple steps that change the number of particles by at most one and sometimes two. Okay, so here we come along here, the electron comes on, it absorbs the photon and produces electron. Or it might be that the electron produces the photon. And it keeps going on and on. So here we have pair creation. Here, and particle and antiparticle, same mass and spin, but the opposite charges, and then radiation processes like this. So again, this little picture here, a single electron unravels itself into a pair plus an electron plus a photon. And it gets more and more complicated as you go. But sadly, or not, for an isolated electron, all of these states have energy greater than the electron's energy by some amount, say some time delta E. And these are the virtual states, a concept of which I'm sure everybody has heard about. It's out there in the popular world. And they live only for a time. And this is where Planck comes back into the game. T is H over delta E. Never mind H bar. I mean, this is the basic idea. The time at which it lives is 1 divided by the extra energy you would need to produce that state. And you could say, well, but these aren't Lorentz invariant quantities. And it's certainly true. If you go to a boosted frame where now delta E is, well, it depends. Delta E may get larger or smaller. The time correspondingly gets smaller or larger. Okay. And after this time, on average, they're wound back in. Like here, the process that we saw before, we have pair creation is followed by pair annihilation. Radiation is followed by absorption. And the electron turns back into itself. And no matter how hard it tries, to the extent one can use this personification, each particle in isolation returns always to itself, only to start over again. But starting with two particles in a state, this is where things happen, and this is what colliders are all about. Starting with two particles in a state, together they have enough energy to produce new states by spending short amounts of time in a series of virtual states. So here we have two electrons coming in, and the virtual state is a photon. So the energy of this state cannot, it can be this, it can't be this the same, because we can think of this one as producing the photon, and then this here wouldn't have the right energy compared to this line. But if it's absorbed by the other particle, then the final state could have different momenta and the same energy as the initial state. The higher their energy, the more states they can bring about. And this is how things happen. For example, X-rays, like at the doctor's office, so to speak, are made by adding another virtual state. So we exchange this photon, and then one of the scattered electrons radiates, and we get to the final state with the same two electrons, now with different energies, and the remainder of the energy going into the photon. So you make one of these a nucleus and the other an electron, and that's how you get X-rays. Okay. So from particles to prediction, a question. Give this man a hand. Thank you. Okay.
You're talking here about kinetic energy, right? Because the complete Hamiltonian has to be, the complete energy of the total Hamiltonian has to be
Yes.
constant.
So we start out typically with kinetic energies that we prepare. We understand it. Here's how much energy we're giving this electron and how much we're giving the other electron, or the energy of a stationary target. Then we may produce new particles in these final states in situations where, for example, a photon could produce a pair of heavy quarks, or a gluon could produce a pair of heavy quarks. work. So some of that energy will go into the production of new particles. And indeed, that's exactly how we get the new particles. Anything else? Okay, well, I have one question. That's pretty good. Okay, so then for each process given by a picture, there are rules to calculate a wave height, that is to say an amplitude, and these are the famous Feynman rules. The amplitude is just a number, okay? Found like this. Okay, so here's an initial state, here's this exchange photon, the state with the exchange photon, and the final state. And it equals the E squared, which is E associated with each of these point-like interactions. And roughly speaking, it's the length of time that this thing exists divided by h times extra factors of particle energy that have to do with luminosity and things like that. And this delta t, this is delta t sub v, that's what this is supposed to mean, is equal to, given that delta t knows about the violation of energy conservation, h is EV minus E initial. So it's the energy of this virtual state compared to the initial state. And that's how long this intermediate state lives. And the beauty of it is, as complicated as these things get, in some sense, the amplitude is literally proportional to the lifetime of the virtual states. It's kind of amazing, actually, how simple it is. Okay, but as soon as you try to calculate the darn things, beyond the simplest case, it gets very complicated very fast because there's so many different virtual states and other reasons too. Okay, so we can estimate the times by using 200 MeV as 1/1 Fermi. We can turn this into amplitudes in a systematic way. So the probability for any process to happen, of course, is proportional to the square of the amplitude, just as the density of photons in a wave is proportional to the square of the electric field. And the electric field is, to some extent, this amplitude here. Whoops. But, for example, here, the amplitude that corresponds to the creation of a muon anti-muon pair from the electron-positron pair in a head-on collision probably is given by this thing squared, and it ends up equaling e to the 4th over 8 pi, just the whole thing. When the muon, so when the muon is in the same direction as the electrons, but equals e to the 4th over 16 pi when the muon is produced at right angles to the electron. In some sense, it's extremely simple. And this is the process on which many, many experiments have been done to test out these theories, starting at this lowest order and working to much higher orders. But of course, whoopsie daisy, it gets more complicated quickly with more virtual states. But in the case of QED, quantum electrodynamics, because E is a small number, E squared over 4 pi is 1 over 137. So E is small, but it's not that small. It's actually like a 10th or so. This prediction is pretty accurate. Just E to the 4th over 8 pi compared to E to the 4th over 16 pi. All righty. Well, anyway, this is quantum field theory. So you got a whole course of quantum field. Well, more or less. But not quite. You say, wow, it has to be renormalized. Okay, that's what we're going to do in this last 5 minutes. We're going to renormalize quantum field theory, and I think that's what's here. Anyway, there's no, okay. Now, here's where this locality concept, this idea that at a point in Einstein's work comes in to this description of nature. There's no limit to how short a time virtual states might live, and therefore no limit to the energy that they might have. So if there is a quark or it has a supersymmetric partner that's 20 times, 200 times the mass of the top quark, then that will live 20 or 200 times less long, shorter than the time a virtual top quark would live. But because there's no limit to how short these processes, time these processes can live, the closer you look at an interaction, the more you will find. And so, for example, suppose we said, well, what we know is we sent in an electron, and then we looked a little while later, like with an X-ray apparatus, and there was an electron plus a photon. And that was the photon that produced the X-ray by scattering off the nucleus, let's say. So here we could say, well, we don't really know where that happened, but it happened in an idealized situation inside some region, three-dimensional region with a radius r. So we could say maybe it happened right there. And we'll say this is the region, but what we know is it came out into this sphere, came in as one particle and it came out as two. But also, this could have happened. Here's our electron coming in. It breaks up into a photon. It produces a pair. Then it produces the photon that eventually we observe. But then this pair says, nah, I think I'm coming home. It produces a photon, annihilates, produces a photon, and comes back to our electron. So we have the same state that we started with, a single electron, the same one that we ended up with, an electron plus a photon, but a whole lot happened in the meantime. Now, it's actually, when you start to calculate these things, you say, well, actually, you know, this could have lived for any amounts of time between the time it takes, like r over the speed of light, okay? So this delta t, it took place inside this sphere, and it has a sort of maximum time it could live, but it doesn't have a minimum time, right? And it turns out that when you try to calculate that, you run into a divergence. The divergence is associated with times that are infinitesimally small, and therefore with energies that are infinitesimally big, high, large, right? So nothing more than that. So the question is then, we know that since the amplitude is proportional to delta t, when delta t gets small, it's like 1 over delta E. So when delta E gets large, it keeps going down. The integrand keeps going down. But we have to ask also, well, that's for one particular state. Say the state in which this pair in the middle here is, well, this pair could be going in the x direction, but it could also be going in the y direction. And come to think of it, it could be going in the z direction. So suddenly we say, oh, wait a second. We have a very, very small amplitude for each direction, but there are many directions. And so what happens is, as we sum over all of the processes that could occur with the high as that violate the conservation of energy by a large amount, we don't necessarily get a convergent sum. And in fact, in all of the theories of the standard model, that sum does not converge. And we need, as a result, to blank these theories. It is not throw them out, these theories. What do? I bet somebody, lots of people have heard this. Everybody. It begins with an R.
Normalize.
Renormalize the theory. That's what renormalization is about. It's about dealing with these intermediate states that have extremely high energy, which individually don't contribute anything, but there's so many of them. So it's our way of dealing with that by doing the following. What we do is, instead of asking what really happens, we take the viewpoint that, well, the world is here, so something happens, okay? So yeah, let's let everything inside the sphere take care of itself, right? There's some other theory that deals with this problem at very, very high energies, but what we can do is we can calculate the dependence of this amplitude, 1 electron in, electron plus photon out, as a function of R. If we choose R, we can't calculate what's on the inside. But if we try to say, what about R compared to R minus delta R or R plus delta R. We can calculate the derivative, okay, with respect to this, the size of this volume, because basically it's only, they're just relatively few particles that, processes that happen right at the edge. And that's enough to make this sum finite. Okay. So what we're looking at then, almost, we're getting there. What do we see? We see, whoops, no. What's that? Okay. You know, I had to go back. Okay. So we can actually calculate how these diagrams depend on R. The result is called a running coupling, and it's usually given as a function of the de Broglie wavelength that corresponds to radius R. So it's alpha evaluated at a momentum scale, which is h over R. Sometimes think of it as a mass scale, but one of these things where we put everything in natural units, multiply by whatever C and H parts so that it has momentum and mass have the same dimensions. In this case, it's just speed of light. Okay, and alpha, the alpha we have in quantum electrodynamics is E squared over 4 pi. So we can get a handle on E and therefore an alpha. For QED, this technique is not such a large effect, and there's not a strong dependence on this P, but it's very important for the strong interaction. So what you do here is you're saying, well, I can't calculate this actual thing that happens in the real world, but I can calculate how it depends on the scale that I choose to define it. Here, the scale is very simple. We say if one electron comes out into this sphere, comes out as an electron plus a photon, that's our amplitude. I mean, so we can calculate how that would change by changing different sizes of the sphere, but we can never take the sphere all the way to zero, because in that case, we'd be swamped, entirely defined by just a subset of the states. So what we do is we say we actually technically we calculate the probability for X-ray diffraction at the doctor's office. And then we bring it back to this and we say, okay, we're going to do this at some R of like 1 femtometer or something like that. And that's our definition of E. Actually, the way it's really defined in QED usually is we take this photon and we take the limit that the photon energy goes to zero, so-called Thomson scattering. And it's in that limit that we can actually measure the electric charge because it corresponds to classical motion. So that's something very special for QED. And that's because E is so small. But for QED, this technique, as I say, is not such a large effect, but it's very important for strong interactions. And that, so what do we see? Sums of states, lists of particles. And this just kind of summarizes everything here in this first lecture. Here we have again this d by dt of sums of lists of particles, the rule for changing the list times the same list of particles. And here's what's happening to any particle in isolation in this picture. And we take away that individual electrons are really collections of just these states and more, but it's still just an electron with some friends. And that's what's going to happen at EIC. The electron comes in with some friends, and one of those friends makes for a scattering. Okay, and with that scattering, it will take quarks who are living there with a lot of friends inside a proton, and what we'll find out is we'll find out the friends that are closest to them. The friends that are closest to them will be the friends that produce jets and heavy quarks and things like that. Okay. So we'll see how that happens. And I believe that brings us to the end of set 2, which was our sketch of quantum field theory and how it could relate to concepts that we've explored experimentally. And then tomorrow we'll talk about what makes QCD different. And in the lectures today, you'll see lots of things about what makes QCD different. And so, this will be, in that sense, a causal. But that's what learning is about, I think, is getting the same concept from different viewpoints as you go along and then combining them for yourself into a meaningful whole, which I hope that this school will give you as the week goes on. Time for a little bit of coffee.
Thank you. Questions or comments to George? Good.
I was wondering why can't we use the same sort of language and techniques to describe gravity?
Well, you can. And in fact, using the techniques that Fred's going to talk about, dimensional regularization, there is a theory of gravity at relatively low energies. So, what happens is, see here, while looking at this, just the first slides, we see one quark coming in and then coming out as one quark and one gluon from this sphere. If you have one graviton again, what you find is that, see, okay, now, if we said, one quark coming in and two gluons come out. Okay, this is a gluon. I forget whether I say graviton, but here it's like one quark state produces one plus one gluon. You could say, well, I'm going to do an R, and how about the calculation of one quark comes in and two gluons come out with a quark? We have to have the quark just for electric charge and other quantum numbers. But when you do that, you analyze it in the standard model, and this is what sets the standard model apart as cool, is that you can reduce that. It turns out that if you say, I've solved the problem of one quark goes to one quark plus one gluon by doing a little r, so forth. Then when I look at all the processes that contribute to a quark goes to quark plus two gluons, I can reduce it to quark goes to quark plus one gluon. And then once I've done that, the whole rest of it is finite. This is characteristic of so-called renormalizable theories. In gravity, let's say a quark comes in, produces one gluon. Then it could produce two gluons. And what you find is you have to do the same game of reducing your calculations of derivative with respect to R to quark goes to quark plus two gluons, or in pure gravity, gravity goes to gravity plus three gluons, also four gluons, also five gluons, also six. So as many different elementary processes as you could imagine in quantum gravity, all of them will require this running coupling approach. However, although what happened was for a long time, people thought, well, that means gravity, quantum gravity is just nonsense, doesn't mean anything, because you have an infinite number of couplings that you would have to renormalize. The higher you go, the more couplings you get. The higher you go, meaning the more virtual states you're willing to take into account. Plus, those calculations are like really complicated. But what happened in the intervening years is this idea of what's called effective theories came about, where you don't expect things to be renormalizable in the sense that we just described, but that you could say, nevertheless, even though these new couplings are there, and I have to use renormalization techniques to define them, nevertheless, if I do things right, I can see that their effect is small until the energy reaches the scale of the theory. And in gravity, that's clearly, it's like 1 over Newton constant, which is the Planck scale. So, of course, the difference is already seen in the fact that the electron, in QED, the coupling is dimensionless in natural units. But in QCD, it's set by the Newton constant, which has dimensions. Now, so that's the difference generically between renormalizable theories and non-renormalizable theories. So it has like 1 over mass kind of, because multiplying M1, M2. So that's really, so what happens is that you can systematically look at these things and treat the theory as though it were renormalizable with the confidence that at low energies, these extra couplings that you induce are in fact small. And this is used to great success in the analysis of gravitational waves, in fact, this whole approach. So that's what happens with gravity. Oh, by the way, one last thing. It's really kind of neat. For a long time, like when I grew up, it wasn't before Einstein, it was close. The renormalizable theories with dimensional couplings, dimensionless couplings, were thought to be like, that's the cool thing, because that's the stuff we can calculate. But if you go back and you say, what did the great minds think? Einstein wrote somewhere, that he didn't think that an eventual theory of the universe should involve any dimensionless couplings, because the dimensionless coupling is like 1 over 137. Where'd you get that from, right? It's just a number. The number could have been anything, but if you change that number, the world is totally different. So it must be based upon something more fundamental. If there were only gravity in the world, then if you change Newton constant by 2, everything like gets bigger or smaller in some sense. Nothing really changes. The dynamics is the same. So in some sense, from many points of view, if you're going to have a finite theory without this kind of normalization process that you do, you need at the bottom a theory with a dimensionful scale. And it should have, if you're really looking for the ultimate, it should have exactly 1 dimensional scale, which would be something like the string tension if you are a string theorist. Okay, and then every other scale, it might be, oh, we're here with alpha equals 1 over 137 because there's some compactification of the extra dimensions, and that's the way the universe decided to go in this particular go around. And so that's where the 137 came out. It could have been 1 over 125 or 138 or 1 over 10 to the 4th, in which case you have huge atoms or something like that. So these differences between the renormalization is not everything. It's sweeping things under the rug, so to speak. And what goes under the rug is what's way, way up in energy. It's things of very, very short times, virtual states of very short times. But even in that case, mostly I would say the real inspiration for this was the work of Weinberg on chiral effective theory, as it's called now, that showed people that we shouldn't be intimidated even by quantum gravity. Another question, I don't want to, okay.
We don't have that. Go ahead.
Oh, no,
Oh, no,
we do.
we don't
I'll
have
be
time. That's the
sure.
whole idea.
No, it's on this. When we're at, maybe it's very stupid, but when we have equity or QCT, renormalization, we use renormalization that these theories are normalizable based on the fact that we want them to be scale invariant or universal to the evolution equations, Artsy flows, and that stuff, right? So then we do, okay, there is new effective theories in this, and we use them, and we know already that these theories are physical because they're scale invariant.
Well,
But
I was scale invariant usual. But anyway,
the question is that, okay, but this is how the normalization basis is up in my head.
and it's just an effective theory.
Yeah.
That's right. So our understanding of the world is an effective theory of some underlying theory.
But in gravity, I don't understand that. Okay, if it's not renormalizable, at least the quantum, the curved QFTs that exist, why we can use effective theories and sort of scales if we don't?
Because the effect of these higher couplings is suppressed by the momentum at which we're probing the theory divided by the scale that sets the theory. That's a theory. And so they're small, they're literally small. They're times some unknown coupling or couplings you can set by looking at the experiment. And the way you look is for effects that increase like the energy. But as the energy goes to zero, their effects will vanish and we just actually end up with Newtonian gravity. Well, we should continue, I think, I'll be here this evening at 7:30 and I think we have to let things move along. So thanks for the questions and I hope we have some more on Tuesday.
Excellent. Let us thank George Michael.
Quick announcement, we put in a request for warmer weather, but in the meantime, they will have blankets at the dorm from 4:30 to 6:30, so you can pick those up. And so should we take 20 minutes and we'll,
Do 20 minutes.
yeah, we'll have a relaxing coffee break.
Both requests will match. Warm weather is coming, but also blankets later today, so you can get those to dorms. So let's have 20-minute break, some coffee discussions, and then we'll have a lecture.
Like you're across the toilet. Having them communicate. Tell you others. Yeah. Sorry about this. Oh, you're in a state, okay.
Yeah.
Oh, not either. Either. Find the right to play shirt. Okay.
And maybe insert
Thanks.
We do. I'm new to this. Or this nuclear based. Sorry, yes, my English was my pronunciation.